Welcome to our help video over the quiz 3B12 on atomic mass. The first 5 questions were true-false questions. First question, 1 AMU is defined to be the mass of one carbon atom, No, that would be false. An AMU is 1/12 the mass of a carbon-12 atom. That means an AMU is pretty small. It's a 12th of carbon's atom. Remember, carbon-12's atom has 6 protons, 6 neutrons. So that means that an AMU is really very close to the average mass of a proton and a neutron, somewhere in there. The mass of a neutron, on number 2, the mass of a neutron is larger than a proton. That is true. Protons are 1.007 AMUs. Neutrons are about 1.008 AMUs. Or if we round it, it would be 1.009 if we round up. The mass of an electron is very small. Absolutely. If you take a look at our numbers right up here, an electron is 0.0005 AMUs, where protons and neutrons are a little over 1 AMU. So an electron is way, way, way less massive. 1 AMU is equivalent to a gram. No. AMUs are very small. Very, very small. An AMU is 1.66 times 10 to the minus 24th grams. That would be like and then it'd be 0.000. We'd have to keep going with about 23 zeros total after the decimal point 1. That is a really small number. 0.000, 000, 000, 000, 000, 000, 000, 000, 000, 166 grams. Number 5, the weighted average of the naturally occurring isotopes of an element is called atomic mass. That is true. Atomic mass is essentially the average of the isotopes. All right, 6 through 10, also true, false. And they are dealing with this little slice of the periodic table here. The atomic mass of arsenic, which is right here, is 74.92 grams. No. 74.92 grams would actually be the mass of 6.022 times 10 to the 23rd arsenic atoms, because that is the mass of 1 mole. And 1 mole is a quantity, and that quantity contains 6.022 times 10 to the 23rd. So what is the mass? What is the atomic mass of arsenic? The atomic mass of arsenic, again, is the weighted average of the naturally occurring isotopes of arsenic. It's not 74.92 grams, it's 74.92 AMUs. A mole of selenium, we're talking about selenium right here, has more atoms than a mole of gallium. That would be false again. A mole is a mole. A mole is a quantity, similar to a dozen, except mole is a lot more than a dozen. A mole is a mole. A dozen is a dozen. How much is in a mole? 6.022 times 10 to the 23rd. So a mole of selenium has 6.022 times 10 to the 23rd. A mole of gallium contains 6.022 times 10 to the 23rd atoms. Now their masses wouldn't be different. Their masses would be different. To have a mole of gallium, you would need to put 69.72 grams of gallium on the balance. To have a mole of selenium, you would need to put 78.97 grams on the balance. Yet the mole has the same number of atoms. Why does it take more mass of selenium to have the same amount as gallium? It's because selenium's atom is slightly larger than gallium's atom. So a mole of selenium atoms would have a mass slightly more than a mole of gallium atoms, because the atoms of selenium are slightly larger. Number 8, 72.63 grams of germanium contains 32 atoms of germanium. No. 72.63, that would be false. 72.63 grams of germanium would have a mole of germanium atoms. It would be 6.022 times 10 to the 23rd germanium atoms if you had 72.63 grams. What's that 32 then? That 32 is the atomic number, which is just saying that a germanium atom must have 32 protons. Number 9, the atomic mass of krypton is 36 AMUs. No, krypton atoms have 36 protons. The atomic mass of krypton is 84.80 AMUs. 69.72, number 10, 69.72 grams of germanium contains the same number of atoms as 78.97 grams of selenium. Absolutely. Those are the molar masses. Those are the molar masses of those substances. 69.72 grams of gallium would have a mole of gallium atoms. And that mole of gallium atoms would have a mass of 69.72 grams, and it would contain 6.022 times 10 to the 23rd atoms. To have a mole of selenium, again, selenium is slightly bigger than gallium. So to have a mole of selenium atoms, we would need a mass slightly larger than gallium's mass. So we would need 78.97 grams of selenium to have a mole, and that mole would contain 6.022 times 10 to the 23rd atoms. 11 through 15, true, false. Mass defect is a process where some of the mass of the atom is converted to the nuclear binding energy. Yes, if you happen to look at the atomic masses of the isotopes of some of these atoms, the atomic mass of those isotopes can actually be less than the mass number. So let's look down here on this chart. Silicon-28 has a mass number of 28, meaning that there's 28 particles in the nucleus. Remember that the protons and neutrons masses are slightly over 1, as we see up here. A proton's 1.007, a neutron's 1.0086, which we would round to 1.009 if we're just trying to shorten the number a little bit. So we would expect silicon, based on just the masses of the protons and neutrons, to be over 28, but it's not. It's under 28. It's 27.97. So where did the mass go? Well, that mass is actually converted to energy. You remember the formula, E equals mc squared, a very famous formula by Einstein. Just shows that there's a relationship between energy and mass. Mass is energy, and that mass, some of that mass was converted to energy to hold the protons and neutrons together in the nucleus. Number 12, small atoms with low numbers of protons are most stable when the neutron-proton ratio is 5 to 1. No, it's 1 to 1. Remember, for those smaller atoms that we looked at, especially in the 3B11 lab, and the lab we did previously, we noticed that the ratios were usually 1 to 1 for the smaller atoms. Like helium has 4 total particles in the nucleus. 2 of them are protons, 2 of them are neutrons for helium-4 isotope. The 1 to 1 seems to be the most stable. Number 13, the atomic mass of isotopes expressed in AMUs can be larger than the mass. Well, for some atoms, it can be larger than the mass because, once again, the mass of protons is a little more than 1 AMU. The mass of neutrons is more than 1 AMU. So the mass number then, if not as much of the mass was converted to the binding energy, the mass of many of the isotopes can be larger than the mass number because protons and neutrons, the mass number is the number of protons and neutrons, that's a whole number, but protons mass and neutrons mass is greater than 1. Number 14, the decimal number on the periodic table of elements is the average mass of the atom expressed in AMUs, and it is also the mass in grams needed to have 1 mole. Yes, it is. That's what a lot of the questions were up in here. This number right here, the decimal number in that box, has 2 meanings. It is the average mass of the naturally occurring isotopes in AMUs. So, for instance, krypton's mass, average mass is 84.80 AMUs. But to have a mole of krypton atoms, we need to put 84.80 grams of krypton on the balance. And the advantage of a mole is we know how many atoms there are. Why is it that that number has a dual meaning? It is because they were both based on carbon-12. AMUs are based on being 1/12 the mass of carbon-12. Molar mass, the mass of 1 mole, is also based on carbon-12 when we look down here in question 15. 12 grams of carbon-12 contains 6022 times 10 to the 23rd atoms. So the whole mole concept is also based on carbon-12. When you base both of them on carbon-12, that gave that decimal number on the periodic table a dual meaning. All right. Now we are going to find, in problem number 1, we're going to find the average atomic mass of silicon, and we are looking here that silicon has 3 isotopes that are contributing to this mass. Silicon 28 is the most abundant of the silicon isotopes, with 92.23% of the silicon atoms having the mass of 27,97693. Again, why is this number less than that number? The mass number is 28, saying there's 28 particles in the nucleus, so we would think this number would be over 28. Again, mass defect. Some of the mass of the protons and neutrons went to holding the protons and neutrons together in mass defect. So how do we do this problem? Well, first of all, we're going to convert these percents back to decimals by dividing by 100, which is the same as sliding the decimal 2 to the left. So the 92.23, we change it back to decimal form to get 0.9223, and we multiply that by the atomic mass of silicon 28, which is 27.97693. We're going to slide this decimal as well 2 to the left. So the decimal goes to the 0.4, and then it goes one more to the left to make it 0.0468, giving that atomic mass of 28,97649. We multiply those two together. This bracket is showing you that this information inside these parentheses is the contribution of silicon 28. Inside this parentheses are the contribution of silicon 29. And inside these brackets are the contribution of silicon 30. Again, change this percent back to decimal by sliding it 2 to the left. So the decimal would go to 0.3. Then it would go one more to the left over to here. We would have to add a 0. 0.0309 times 29.97377. Plug this into your calculator. You can use parentheses on your calculator to make it very easy. Parentheses 0.9223 times 27.97693 parentheses plus, and then another parentheses, and plug those numbers with the parentheses plus the parentheses, plug those numbers in with the parentheses, hit equals. You get this long number here. We probably should round this to 3 places, since these numbers only have 3 numbers, since 4.68 and 3.09 have 3 numbers. But we can assume here that this is, we're just going to round it to 28.09, because that's what the number is found on your periodic table. That's really why I did it, so that if you were matching against your periodic table, you could see the same answer. But remember, when we round, you always pick the number that has the fewest numbers in it, and that's how many numbers you keep in your answer. So I could see where you would round that to 28.1. I would be great with that. In our next video, we will pick up with problem 2 and problem 3.